I realize that I am the only thing standing between you and an after party. So just keep that in mind. Just 30 minutes, that's it, I promise. Hi, everyone. I'm the last talk of the day, so I'm gonna need a response from you. Hi, everyone. Awesome, I love it. Okay, hi, my name is Vaidehi. I am an engineer at a company called Tilde. We build Skylight, which is your favorite Rails profiler. So if you need a profiler for your Rails app, come talk to me after. I am an engineer based in Portland, but my background is actually not at all in software, and I come from a very non-traditional, non-CS background. And one of the things that I've kind of learned throughout my career in writing not just Ruby, but all sorts of code, is that we can't agree on a lot of things, but one of the things that we can agree on is that there are many ways to do things. There are a lot of different ways to approach problems and to solve them. If you don't believe me, go look at the JavaScript ecosystem. So there are a lot of different ways of doing things, and what I've learned is it's not just with code and it's not just with frameworks and languages. This holds itself to be true at the lowest possible level of code. What I'm talking about is computer science. And I recently learned that there are a lot of different ways to write numbers. It just depends on how many digits you want to use. So let's start simple. We can write things with 10 digits. And this is the counting system that most of us learned in elementary school, right? 0 through 9. This is actually called base 10. Cool party trick if you want to impress someone. This is also called the denary number system. And then you can really confuse them and then start counting like up to 10 and then be like, I'm counting in denary. I've not tried this, so if it doesn't work, I'm sorry. Maybe it's not a good party trick. But for example, you can write the number 205 in denary in base 10 as 205. But you can use a different number system to represent the same thing. You can use 2 digits to represent 205 using something called base 2, which many of us know as binary. So how would you represent 205 in binary? Well, turns out it is 11001101, which is kind of a mouthful, but that's 205. But more than one way of doing something, right? You can also represent 205 using 16 digits. This is called base 16, or the hexadecimal number system. But how do you represent that? We only know 10 digits. How do you do that? How do you do 205 in base 16? Well, to answer this question, I think the fundamental thing we have to answer first is, what do we mean when we say base? Base refers to how many possible digits you can use in a single place value. So let's deconstruct that a little bit more. Base 2, 2 possible digits that you can ever use, and that's it, 0 and 1. Base 10, 10 possible digits you can use. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Hold on, it's going to get slightly more complicated. Stay with me. Base 16, we need 16 digits. Well, we'll use the 10 that we know. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Except we still only have 10. We need 6 more. We can get a little creative and use A, B, C, D, E, F. For the purposes of this talk, those are all numbers. That's just what you have to imagine for the next 26 and a half minutes. And then they can go back to being letters again, but 26 minutes. So base 16, how can we represent 205 using 16 possible digits to work with? Well, 205 in hex is CD. I'm not kidding. Really it is. I looked it up, I promise. It's really what it is. So, 205 represented 3 ways. There's another interesting pattern here in the 3 different base systems that we've looked at, the 3 different number systems. When we used base 2, and only use binary, we needed 8 digits to represent this one number. When we use base 10, we needed 3 digits, so that's a little better. But in base 16, we only needed 2 digits, which is kind of cool, and it's going to come up again in a moment. But there's a pattern there. So, okay, cool. Patterns are fine, but like, why does this matter? Well, it turns out it all comes down to space. And as programmers, we try to be efficient and think about space and be cognizant of how much space and time we're using, or at least most of the time we are. But if you have the number 205 represented with these 8 digits, one of these digits is called a bit. Another cool party trick. This talk is filled, like, I guess, if you learn nothing from this talk, at least you have these 2 party tricks to use. One bit in this set of 8 numbers is also a binary digit. That's what bit is short for, binary digit. 8 of these bits represents 1 byte of information. So if 8 digits is what you need to represent 1 byte, that's fine, but if you could represent the same amount of information with just 2 digits, that's pretty cool. You're saving like 6 digits of space, which doesn't seem like a lot, but it adds up. So the idea with hexadecimals and what makes them so powerful and so widely used in computer science and in the software that you and I write is that the fewer the digits, the more information you can actually pack into a tiny amount of space. And we'll see how this is used all over the place. And it is why 16 is my favorite number. So, how many of you ever have had to write CSS? Wow. Someone raised their hand and their face just sunk down. Like, I totally identify with that. So, okay. Let's do a quick poll. If you had to represent a color in CSS, how many of you would use this syntax to do that? Okay, and how many of you would use this syntax, the one on the right? The one on the right. Oh, okay, there's a couple. Okay, cool, I saw a couple hands. Well, no need to agonize over which side to choose because these 2 are the exact same. And it turns out that it's hexadecimals operating under the hood that makes them equivalent. So, both of these colors actually represent this red. And if we look at the hex code for this red, it is EC1523. But let's unpack it one little bit at a time. We'll look at the first 2 consecutive hex digits. You'll remember 2 hex digits represents 1 byte of information. So, the first 2 digits, 2E, if you turn that from hex into base 10, is actually the number 46. 15 in hex, when converted to base 10, is 21. And EC, when converted from hex to base 10, is 236. Do these numbers look familiar? I hope so, because they are exactly what makes up RGB. We have EC is 236, 15 is 21, and 2E is 46, which is exactly how we wrote the same color using the RGB model. So, all of this in 3 bytes. What's interesting about the RGB model is that we're basically telling our machine how much red, green, and blue to add. And the RGB model is something that is used in like TVs, your monitor, your smartphone, and it comes from the theory of trichromatic color vision, which is basically the idea of additive color. You add a color and you tell the machine how much of a color you want, and by adding certain amounts, you create another color from it. So if you compare this back to the hex code we were looking at just a moment ago, the lowest possible digit for hex is 0, and the highest possible digit after 9 is A, B, C, D, E, F. So if you want to remove all the color, if you want the absence of color, you can kind of think of it as like a volume knob on a TV. You want to turn down all the red, the green, and the blue, which means you want the lowest digit of hex. This is why, if you're ever writing CSS, you can use 6 zeros to represent black. Conversely, if you want to add all the colors and create the color white, you'll dial up all the way to the highest digit of hex, which is why white is represented as 6 Fs. Just hexadecimals operating under the hood. So, what's actually happening with this hex code? We looked at one color, but if we write CSS, we can represent tons of different colors, right? So there's some math going on here too. We have 3 pairs of 2 consecutive hex digits. Got my numbers all over the place. And each of those represents 1 byte of information. Remember, we can have 16 possible values for each of these digits, because we're working with hexadecimals. So let's look at EC, for example. 1 byte of information. 16 values that could be in E, and 16 values that could be in C. So that means in this 1 byte of information, we have 16 times 16 possible permutations, which is where, if you've ever noticed, if you've ever written like RGB color and you've accidentally typed like 256 instead of 255 and gotten like a crazy CSS error and gotten really confused, this is why, because you can only have 256 permutations and it starts with 0. So you can have 0 through 255. So if 1 byte of information can contain 256 possible values, how many possible values could we have for every single hex code, all the colors? Well, I don't know if your math is better than mine. I had to pull out a calculator for this. 256 times 256 times 256, which is over 16 million colors. 16 million colors in the color spectrum that we are compressing down into just 3 bytes of information, which is pretty rad. But I'm also a color nerd, so maybe I'm the only one who thinks it's rad. I don't know. The thing is, though, that hexes are everywhere. So even if you don't write CSS or have no desire to, you're interacting with hex codes or hexadecimals all the time. You just might not always realize it. So probably the one that you interact with the most is encoding. If you're not very familiar with encoding, which I didn't really know how it worked for a long time, and now I have like an analogy in my head. Encoding is basically like translating between different representations. So you can kind of think of it as like a Rosetta Stone, except nobody's chiseled it into a stone, and it's definitely not in the British Museum. But the ASCII table is probably the most commonly used encoding scheme that all of us interact with, or will interact with at some point. And the ASCII table has 95 different human readable characters. And what that means is there's like lowercase letters, uppercase letters, interesting symbols, but there's also like tabs and spaces and all the things that your machine would need in order to take a string and interpret it for what it is. The interesting thing about ASCII is that you basically are using it kind of like as a Rosetta Stone, and it gets translated from a string to hex to binary. So for example, if we wanted to translate and use ASCII encoding to turn Ruby down into the very nitty-gritty binary of what it's going to be, the string Ruby using ASCII encoding would turn into this as hexadecimals. R maps to 52, U maps to 75, B maps to 62, and Y maps to 79. But our machines don't run on hex, they run on binary. So there's another step we have to do, which is we have to turn these hexes into binary, which looks like this. And I am thankfully not going to read it to you, because it's too many ones and zeros. But you'll notice something interesting, which is that the first digit of each of these 4 binary representations is unused. There's all zeros and they're empty, which seems like an awful waste of space because we anyways need 8 bits to make a byte, and we're not using that digit at all. Actually, it turns out I'm not the first one to think of that. The Europeans thought of that, and they were like, oh, this is silly. We have all of these characters, and like, look at these Americans. They're not using everything they could. We're going to use that last digit. And that's exactly what they did. They used that 8th bit, and instead of 128 possible representations in the ASCII table, they extended the table. And by doing so, by using that last bit of information, they actually allowed for 256 different characters that could be encoded. And this is actually what the extended ASCII chart looks like. And you'll notice that there are some interesting characters in there, and we start at 128 and go all the way to 255, which is pretty smart, and Europeans definitely beat us in that regard. But it turns out hexes are used even in crash reports, which is really cool. So you might have heard of leet speak, and leet speak is actually derived from something called hex speak. And hex speak is basically like magic debug numbers, and programmers like, I don't know, even I think as far back as the 80s, maybe even before that, would use like these little bits of hex that they could turn into easily recognizable words. And they decided, we're not gonna use it for anything else. We're gonna use this to represent like something going fatally wrong in our program. And you might have actually seen some of them. Here's one of my favorites, boo dead, which actually I found out the OX prefix means that this is a, like a magic, it's a hex speak that's used in the C programming language. So if you ever see the OX prefix, it means it's used in C, apparently. Boo dead is one hex speak code that is used to signify when the HP 9000 model 840 crashed. That doesn't mean anything to me. Maybe it means something to you. Seems bad. Deadfall is another one, which some of you, I'm sure, have caused. Deadfall is a hex code that is used when a user force quits their iOS application, and then you send a crash report to some developer at Apple who looks for Deadfall, I guess, and is like, oh, that's what happened. Another really fun one is disease. This one's actually not like bad. It doesn't signify a bug or a crash. It just indicates regular boot up for Nintendo GameCube or Wii consoles. So that's cool, I guess. It's a thing. But hexes are also in your IP addresses, which is really cool. In the 90s, somebody really, really smart, or just more aware than everybody else, realized that we were going to run out of unique IP addresses for everybody, and they were like, oh, we should probably stop using IPv4. So they did, and then they created IPv6, which is 8 groups of 4 hexes, and each group takes 2 bytes or 16 bits of information. And it might look something like this, so you can see that the colons denote each of these groups. So every 2 bytes is separated by a colon. So you can probably look up whether your machine is running on IPv6 and what your IP address looks like. It's a bunch of hexes, spoiler alert. And surprise, surprise, hexes are all over Rails too. If you've ever had to deal with sessions, which in my opinion are just terrible, but important, but terrible, they also use something called session ID, which is a unique string and looks like a bunch of garbage, but it's actually a hex code. And if you look at the Rails docs, you'll actually find that the session ID is a 32-character long hex code that's randomly generated. So if you do the math, that's 2 to the power of 32, which I don't know if anybody is really good at math. That's over 4 billion possibilities for a session ID at any given time, which is pretty cool, but also I can't think that big. But session ID uses hex, and it's pretty important to dealing with cookies in a Rails application. If you've ever had to store a UUID or generate a string that's unique, you've probably worked with Ruby's secure random library, and secure random hex, as you would imagine, generates a hex code. There's also, every single time you generate a new Rails app, there's something called an app secret, which is also a hex string that's generated and used to help keep track of cookies and just general security in your Rails app. That's also just a hexadecimal. So I think the really interesting thing is that none of us actually type binary into our machines, thank God. Can you imagine like how many typos would happen? Like I can't even look at that for too long. We don't type binary, we actually use this abstraction. We use hexadecimals as an abstraction and as a really clever way of keeping a certain amount of data in a really small amount of space, which is really rad. And sometimes hard to see if you don't know that the abstraction is there. And the thing with abstractions, especially in the realm of computer science, is that they're really powerful and necessary tools. Abstractions were created by someone who realized, you know, maybe everybody else doesn't need to go through the pain of thinking about this. I can abstract this into like a black box and it'll just work, and then every other developer can go and be productive, which is really powerful and pushes not just our field and our language and community forward, but all of software. The trouble with abstractions is that sometimes they can be used as weapons. And what I mean by that is that people can use them as a way to keep you from understanding. So, there was a talk earlier today that talked about how knowledge is power, and people are very aware of that. So if they don't give you the knowledge of pulling back the curtain on an abstraction, they deny you that power. And I'll give you an example of how this happened to me recently. About 3 weeks ago, the organizers of Windy City Rails were very lovely, and they tweeted out that I was going to be speaking about hexadecimals, and I was very excited. And I woke up that morning to see, after 20 minutes of tweeting this, that somebody had responded to this conference talk, and they were like, I don't mean to shit on anyone, but is this worthy of a conference talk? This is week 1 freshman computer science stuff. Which says a lot, because aside from the fact that you're saying a lot about the organizers of the conference and the attendees, there's an implicit meaning here, which is that if you don't understand this abstraction, then you don't deserve to be in this room, which I wholeheartedly disagree with, because I didn't understand this abstraction until recently, and I know that I deserve to be in this room, as do all of you. So, I hope if there's anything you take away from this talk, aside from my 2 little party tricks, is that you should never allow other people to intimidate you with abstractions. Because they will try to, and they will assume that you won't have the ability to pull back the curtain and understand what's going on. Instead, use abstractions as a tool to empower yourself. And I say this because our field, especially computer science, is filled with abstractions, and that is part of what makes it so powerful. But you have to watch out for those people who are going to tell you that you can't understand them. And at the crux of all of this, I think it really just lies in this one fact. Abstractions are just that. They're just abstractions. They're not magic. People will tell you that they're magic, and they'll obscure them away and put them in this black box, and I think that's especially true in computer science. There's this term that I recently became acquainted with called the gatekeepers of CS. I've met a couple of them on the internet. They could be friendlier, I guess. My response to that is that you should totally tear down that gate and make way for yourself, because as we've learned from the machine learning talk today and all the conversations around diversity, you can't wait for somebody to open that gate. You just have to knock it down yourself, in my experience at least. Abstractions are not magic, but understanding them is what makes them magical. It's what empowers you to understand the code that you write and the industry that we work in. So, if you're interested in abstractions or learning about cool computer science things, as I mentioned, my background is not in computer science. My background before software was writing, and every year I do a weekly writing series. And this year I am writing about the basics. It came to my attention recently and nobody knew it was a pun, so I'm trying to be more obvious about it. The base CS, okay. I'm writing about the basics of computer science, and I publish every Monday, and I hope to make computer science a bit more accessible to people, so that nobody can lord over you the fact that you don't know what a hex code is, because now you do. And hopefully this talk has been worthy of this really lovely conference. Thank you so much.